Good morning, everybody. First of all, I would like to thank the organizing committee to give us the opportunity to present this work online, even if the Congress has been cancelled. It is a great chance to share with you today my presentation dealing with the contribution of organic chemistry to the quantification of active compounds in wine and their deciphering, their biosynthesis. As you likely know, wine is a very complex matrix. This complexity is due to the huge diversity of grape variety, more than 1,200, combined with hundreds of terroirs and many viticulture techniques. In addition, winemaking processes are also very different and increase the complexity. Just an example for the diversity of the microorganisms that can be used for the vinification process. Winemaker can have more than 350 commercial yeast available and about 60 bacteria strains. All this leads to a compositional diversity and complexity that make the compound identification and accurate quantification very difficult, and also decipher that biosynthesis can be very difficult. In this context, organic chemistry can be a very efficient tool to provide us with analytical standards for identification and quantification. The general requirement of those internal standards are their similarity in terms of physico-chemical property, and that they do not contribute to the analyte signal. Only small amounts of standards are necessary, and stable isotope label analog or diastereoisomers can improve the accuracy. I will highlight this possibility given by organic chemistry using some examples: FURANEOL and HOMOFURANEOL, HYDROXYCINNAMOYL tartrate, OCHRATOXIN A, THIOL precursors, and VARIETAL THIOLS. Organic chemistry can also allow us to synthesize larger quantity. To use those compounds are tracers for the understanding of the biosynthesis pathway and filiation between compounds. This lies on the addition of exogenous compounds that can be monitored separately from the target, but with similar structure and or physiological and chemical behavior. Obviously, larger quantities are required in this case. Stable isotope analog are still a good candidate, and I will illustrate this possibility with the THIOL precursors biosynthesis investigation. So, first example, this is related to FURANEOL and HOMOFURANEOL in wine. Those two compounds are free aroma compounds that are present in wine with odor perception threshold at 10 and 37 micrograms per liter, respectively. They confer to the wine strawberry jam notes, and additionally, FURANEOL was also identified as a fruity enhancer. Their analysis is very difficult due to their thermolability, their hydrophily, and also their GC behavior. And in this case, stable isotope dilution assay is the most convenient method to achieve an accurate quantification. I display you on the slide the synthesis of the deuterated HDMF, HOMOFURANEOL. We have deuterium exchange in alkaline condition, and then a back exchange of the proton in a non-losable position to provide us with stable deuterated furaneol. This is a very fast synthesis with a good yield, and the analogs of furaneol but also homofuraneol were used to develop a reliable analysis of their level in wines. My second example deals with hydroxycinnamoyl tartrates. You know that those natural phenolic acids are present in grapes under different form depending on the nature of the substituent. Transcaftaric acid, transcutaric acid, and the transfertaric acid are the three main phenolic acids found in grapes. They are substrates of the polyphenol oxidase in must, responsible for musk browning, but are also involved in the wine oxidation. They are present at low quantities, ppm in must, ppb in wine, and internal standard can be very convenient to improve the accuracy of the quantification. The problem of the synthesis of those esters relies on the high polarity of tartaric acid and also caffeic acid in the case of the caftaric acid. So we develop and patent synthesis with protection group on all the polar function that allow to perform the esterification in an organic solvent and to obtain the various compounds after deprotection. We obtain the labeled cinnamoyl tartrates, hydroxycinnamoyl tartrate, together with the diastereoisomers. Those compounds were used to develop analysis of those compounds, and I display on the slide the chromatographic signal obtained using the diastereoisomers as internal standard to quantify the transcaftaric acid. You can see that there is a very good separation, and we obtain a very satisfactory analytical performance using this diastereoisomeric dilution assay. My third example is related to OCHRATOXIN A. You know that this is a contaminant of grapes, a mycotoxin formed by Aspergillus carbonaceus, broadly found on coffee, resins, cereals, and also on grapes. This mycotoxin is responsible for the Balkan disease, which is a kidney pathology, and that's why a limit in wine was fixed by regulation at 2 micrograms per liter. So there is a need of a high accuracy of the quantification. We developed the synthesis of both diastereoisomer and label analog of OCHRATOXIN A with the non-originality that lies on the labeling position, since we managed to have the labeling on the coumaric moiety, which is different from the previously published method with a labeling on the phenylalanine moiety. This positioning allowed us to monitor the degradation of OCHRATOXIN A into OCHRATOXIN alpha with the loss of the phenylalanine moiety. We use those two types of internal standards to develop the method, the quantification method, with the addition of the standards in a model must and the analysis in LC-MS-MS after immunoaffinity extraction. You can see in green that the use of the deuterated analog allowed us to achieve a stable isotope dilution assay with a very good accuracy, excellent repeatability and reproducibility, and a very low limit of detection, below 15 picogram per liter. For the use of the diastereoisomer compounds as internal standard, we didn't obtain good results, but this is due to the selectivity, the high selectivity of the immunoaffinity to the natural conformation of OCHRATOXIN A. So we don't have a good absorption and elution of the extraction of the internal standard. But you can see that the separation between OCHRATOXIN A and its non-natural diastereoisomer is even better than for the stable isotope analog. So there is only a change of purification to achieve a very good quantification using diastereoisomer dilution assay. Last example is dealing with varietal THIOLs and their precursors. You know that those compounds are considered as key compounds in the wine aroma, and we identify mainly three key compounds: the 4-MMP, 4-mercaptophenol, the 3-MH, 3-mercaptohexanol, and its acetate, the 3-MHA. Those compounds are generated only during fermentation throughout a specific CS liase activity of some yeast strains, and from thiol precursors that are present in must. For the mainly cysteinated conjugates and glutathioneolated conjugates. There were various challenges to overcome, and we dedicated a PhD thesis to answer at three different points. The first one was the identification of new precursors, since the precursors already identified do not systematically explain the whole quantity of 3-MH. We also develop an accurate quantification either of 3-thiols and of their precursors that were needed, since 3-thiols are at PPT level in wines and are in addition very reactive, and for the thiol precursors they are at quite low level in must. The third point was to answer to this question: what is happening in the must during fermentation? And indeed, the investigation of the possible conversion between the various precursors due to their structural similarity. And once again, to overcome the three challenges, organic synthesis can help. At the beginning of the PhD thesis, the three different compounds were identified: glutathioneolated conjugate, or 3-MH in this case, and cysteinated conjugate that were identified in must as thiol precursors. And more recently, the cis-gly dipeptide that could be issued from glutathione. only glutathionylated 3-MH and cysteanylated 3-MH were formally identified as thiol precursors during fermentation. So obviously the question was about the presence of the other dipeptide possibly issued from glutathione conjugate, that is to say the gamma-glucis 3-MH, and also on its potential role as thiol precursors. In order to identify these new 3-MH precursors, we synthesized the gamma-glucis 3-MH and injected it in LC-MS in parallel to a Sauvignon Blanc must. You have here in green the chromatographic signal displayed by the analysis of the synthetic gamma-glucis 3-MH with two peaks corresponding to the two diastereoisomers and a determined ion ratio typical to these compounds. The injection of a Sauvignon Blanc must in the same analytical condition gave us to observe the same peaks at the same retention times and presenting the same or very similar ion ratio. That is a formal proof of the presence of gamma-glucis 3-MH in one grape must. We included all the dipeptide conjugate to 3-MH and 4-MMP in an analytical method together with the glutathionylated and cysteanylated precursors and managed to have in the same run a very good separation of all these conjugates and their quantification with a very good accuracy. In addition to this accurate quantification of precursors, we also focused on the thiol quantification since those compounds are very reactive and can be present in the must or in the wine under reduced form, that is to say thiols, but also under their oxidized form, that is to say disulfides. So we developed a strategy to firstly quantify the reduced thiol by a direct derivatization in the wine of those compounds and their analysis in LC-MS. And in a second time, the same analysis by derivatization and LC-MS separation, but after a reduction step. That this second analysis gave us access to the whole thiols, that is to say disulfides and reduced thiols. We applied this analysis on several experiments, and I give you the example of that show the interest of taking into account the disulfides level. You can see on the graph that taking into account only the free reduced 3-MH, experiment 1 and experiment 2 could be considered as very different in terms of thiol formation. But actually, if we include the disulfides quantification, that is to say applying the second step of the analytical method, you can see that the global level are very similar, and then there is no difference between experiment 1 and experiment 2. So using only the free thiol quantification lead us to give a wrong interpretation to this experiment. The last point is the question, what is happening in the must during alcoholic fermentation? You know that glutathione-elated 3-MH and cysteine-elated 3-MH are thiol precursors, but we didn't have any clue about the potential conversion between glutathione-elated and cysteine-elated conjugates and between the dipeptide and the dipeptide conversion. So we used a large amount of the corresponding deuterated conjugates, and after their addition in the must and fermentation, with the monitoring of thiol, but also of the different conjugates, we determined that glutathione-elated 3-MH is able to be converted in the must into cysteine-elated 3-MH, and this is also the case of the cis-gly 3-MH. There is also a very small conversion of the glutathione-elated 3-MH into the gamma-glucose 3-MH, but we didn't observe any conversion of the glutathione-elated conjugate to the cis-gly conjugate and of the gamma-glucose conjugate to the cysteine-elated conjugate. The second question was about the precursor role of the dipeptides we identified. Using the same strategy, that is to say addition of the deuterated compounds and their monitoring together with the thiol release monitoring, we prove that cis-gly 3-MH and gamma-glucose 3-MH were direct precursors of 3-MH during fermentation. In conclusion, organic synthesis is a very efficient tool to provide us with analytical standards for identification and quantification, and the different examples I gave you illustrate this possibility in various fields of the wine analytical chemistry. But organic synthesis is also able to provide us with tracers that are very potent tools to understand mechanism of and biosynthetic mechanism and fluctuation. And I think the thiol precursor study is a good example of this potency. So we have a good example in which upstream research can provide us with powerful tools to answer to different questions that are of interest for the winemaker. I want to thank all the companies and organizations that were involved in the various study I presented you, and to thank you for your attention.